Greetings. So as maybe an interlude, I thought I would discuss the two capacitor paradox. And whew, this is going to be a super advanced level video. No, just kidding. This was actually, when this occurred to me, it was so stupid and so simple that I literally shoved it out of my consciousness for months. And it kept bubbling up, and I kept saying, no, I'm not trained in this area. There's something I'm missing. And it finally, as it continued to keep bubbling up, I finally said, no, there's actually something weird there. And I want to see if I can understand it. And when I looked on the internet, it's called the two capacitor paradox, and all of the explanations of it are absolute bullshit. So we'll discuss that, and we'll also explain the two capacitor paradox and how it abnegates conservation of energy. So here we have two capacitors, and these are I don't know, they're like maybe 200 volts or something like that, but they're 1,000 millifarads. And I've taken the negative, because they're polarized capacitors, so I've taken the negative leg of each of them and connected the negative leg. So now what I'm going to do is charge this capacitor to 10 volts. Then, if I take a line from this positive and connect it to there, since this is already connected, the two will then be in parallel. And, I'm going to disconnect the power supply first. So I'll charge this cap to 10, discharge it into a second cap. And what do the two caps end at? Well, since each cap is the same size, I think people would say, well, if this one's at 10 and it goes into another one that's empty at 0, and they're both the same size, they both end up at 5. And we're going to demonstrate that that's in fact the case. So I want to be perfectly clear here. There's a few wires running around. What's being done is absolutely simple. This capacitor is being charged, and then it's being connected in parallel with an empty capacitor. And so it discharges into the empty capacitor. And what did the two end up at? So there's the positive and the negative from here to see what's in this capacitor when it starts and when it ends. And then there's the positive and negative from the power supply, which will charge this to 10 volts. And then I'll disconnect the positive of the power supply so that it's only the cap. And then this positive will go boom, I'll connect that, and then the two are in parallel, and this one will discharge to there. So you're discharging a full cap into an empty one. That's all. That is all. Okay, so the capacitor, it's at 10.02. It's hard to get it exact, and when we disconnect this, the cap will be ever so slowly draining out. They're fairly big, but they'll still drain out through the 1 mega ohm resistor in the meter that's measuring things. So get rid of this. And if this, whoa, that's discharging quickly. Yeah, I didn't realize it happened that quick. Okay, so let's do this a little quicker now. That's what I'm talking about with the thing discharging. These are 1,000 ohm. It's surprising it discharges that quickly. But, okay, so, and discharge. So we can see it still just draining out through the meter. And that's what you run into with capacitors. They drain out through the meter. But what we demonstrated, just to do it again, is this is at 10 volts. Quickly. Oh, come on. I don't know what I'm doing wrong there. It's as simple. It's the most simple thing in the world. Okay, so 10 volts, it's charged, gone, discharging. No. Oh, because I never discharged this cap again. Forgive me. So, mea culpa, mea culpa, mea culpa. You actually, you have to discharge this and empty it before, when this one is filled, you put it there. I have made my mistake. What a beautiful mistake is this mistake that I have made. So let's do it again. We charge this to 10. Come on. Charge this to 10. We're just charging a cap and discharging it into another, if I can keep the thing on there. Discharge. Ah, it's caught. It's working against me. What the hell am I doing? This is crazy. So 9.75, so now 4.86. So you can see they both end up at half. And if we move the meter over to this one, we would see that they both equalize to the same voltage. So this one starts out at 10, this one is at 0. You connect them in parallel, they're both at 5. So it's like, no shit, Sherlock. So here is the definition for energy stored on a capacitor. And so energy, blah, 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 1/2 CV squared equals 1/2 the capacitance times the voltage squared. So let's put in a spreadsheet what happened. So here we're saying E equals 1/2 CV squared, and I showed a website that noted that, and it's not a matter of dispute. That's the definition that is widely, I would say universally, absolutely universally accepted for what the energy in a capacitor is. So the voltage in cap 1 was 10 and the capacitance was 1,000 millifarads, so we'll call it 1 millifarad. 1,000 microfarads. What the hell is it? Capacitor is 1,000 microfarads, so I'm just calling it 1 for 1 millifarad. So therefore the energy will be equal to 0.5 times 1 millifarad times 10 and it's squared just what the heck's going on, and then times 10 again. So just to show that, because I don't want any, 0.5 times the capacitance times the voltage times the voltage again to make it squared. So 50 millijoules. This is 1 millifarad. So, again, this isn't brain surgery. This is, cap 1 is at 10 volts and it's 1 millifarad. Energy is 1/2 CV squared. Therefore, energy is 100 times 1/2 times 1 is 50 millijoules. Energy here is 0. Total energy equals boom plus boom there. So now let's look at the ending state. So here's the ending state. they both ended up at 5 volts, remember? And they both are 1 millifarad. So 5 squared is 25 times 1 is 25, divided by 2 is 12.5. So there's 12.5 in that one, and then there's 12.5 in the other. So the total energy equals this plus this. 25, 50, 25. Rut roll. That's the problem. That's the two capacitor paradox. Half your energy was lost, but all you did was discharge one capacitor into another, and half your energy, poof. So there's a couple avenues we could go here. One is we could look at all the bullshit explanations. Sorry, I shouldn't swear. The bullshit explanations. Or before we do that, let's discharge a large cap into a small cap and a small cap into a large cap and do this same thing. And then we can further see what nonsense the explanations are. But just to be clear, half of your energy was lost moving from one place to another. Nothing transformed. There was no transformation. There was nothing. Half the energy gone. Okay? That's that. Sorry if I'm being a little frustrated. Okay, so now we have the exact same setup where this is at 10 volts, and I'll disconnect this and then I'll discharge this, but now this is 1,000 microfarads going into 100 microfarads. So what are those going to both end up at? And I'll tell you what the answer is, that they should both end up at 9.09, I think it's 0.09 repeating volts. And we'll explain why I know that later. Just as sort of an unrelated pro tip, when I disconnect the power line here, you'll now see that this cap no longer discharges quickly or if at all. And why is that going to be? Because I took this cap and I just charged it to 50 volts and I left it there for 20 seconds. And then I discharged it. And there is a memory in the water. And, you know, I'm not talking about like the water remembering Beethoven's Fifth. I'm saying that the dipole on the water molecules, this is a waterlogged capacitor, these electrolytics, they have water in them. And the dipoles all arrange. So now if I disconnect, you recall how quickly it went down. Now I'm disconnecting. And that's what you get now, as compared to what we saw before. So that's just as I said, a unrelated, interesting pro tip. But that makes it easier. So what we should see now is about 0.91 volts, but you know, we'll look, I'm sorry, 9.1 volts. You know, if it's 9, then that's in the ballpark, but right around there, and I'll explain why I know that. Come on. But you know, it just needs to be 10 to be accurate. 9.05. So I said 9.09. So very close. And of course there's 10% or 5%, I can't remember what exactly the manufacturer said for these variants on each of these caps. So we are right there. So 9.05. Okay, so now we put this in with our experimentally derived values. So 10 volts, 1 millifarad, 0 volts, 0.1 millifarads. And so again, the starting energy was 50 and this was 0. They both ended at 9.05 experimentally. And as I said, theoretically they'd be 9.09, and it's probably because of the variance in the actual capacitance versus what the manufacturers put out there. There's usually 5% variance or something like that. So 9.05. So 9.05, and that's the energy there. That's the energy there. So let's go back here. When they were both the same size, went 50 to 25. So let's just do this. 25 divided by 50 equals, we lost half the energy. Now let's do this, and 45 divided by 50. We only lost 10% of the energy. Isn't that odd? So we lost 50% of the energy when they were the same size, and we lost 10% when it was going from a large cap to a small cap. So let's now go from a small cap to a large cap. And I'm going to put this small cap at 50 volts for a while to hopefully it won't drain out too quick before we can get a good reading. So I left this little cap at like 45 volts for a minute. And now if I disconnect it, you can see it still doesn't go down that quickly. That's slower than the cap 10 times its size went down before the conditioning. So, all right, so I discharged the large cap for a while. I'm now charging the small cap. When the small cap goes to the empty large cap, it should end up at 0.909 volts. 1. But again, there's not only the difference between the two caps, there's also the cap rebound, as it is called, which is the conditioning of the caps to the voltage that they were previously at. But we saw 1 volt, and look at him go. See, that's cap rebound. That's because the water is polarized in the previous direction. I left it at 50 volts for like a minute, and so it's just climbing in voltage. That's neither here nor there. So it's 1, but the textbook answer, if everything was arranged correctly and if there was no cap rebound going on, would be 0.909 volts, but we'll put in 1. And you thought it was simple, just discharging one cap to another without anything else. Maybe I did, maybe you didn't. So, all right, let's put this in. I haven't done it yet. Let me do it. Okay, so we put that in, and we were at 10 volts with the small cap at 0.1 millifarads. And so we have 5 microjoules of energy there, 0 in the other, and that's the total. Now, that's what we get for our total at the end. So at this point, experimentally, we lost 89% of the energy. And again, it's actually going to be worse than that without the cap rebound. So, depending on whether you're discharging caps that are the same size, or a large cap into a small one, or a small one into a large one, you lost 50%, 90%, or let's say 10% of, you lost 50%, 10%, or 90% of the energy. So here's a write-up I've been working on, and perhaps I'll release this as a booklet or a book at some point. But I'm talking about my going through this and my having finally accepted there was a problem there and that there was a paradox. So at this point I was reassured that what I had noticed was indeed a paradox, and was hopeful that I would now quickly find a reasonable and well-supported explanation. The issue was first publicly brought up, at least as early as 55, by Zucker in an article entitled Condenser Problem. Condenser means capacitor. Followed by Levine in 67, apparent non-conservation of energy in the discharge of an ideal capacitor. And then in 2019, Kirk McDonald sort of did a review, and he notes some 42 citations over those interviewing years dealing with this question. So it's not like that I'm the only one who's noticed this. And here's what McDonald said in his article, just to be clear. The paradox is that the final stored energy, is this. Hence, half the initial energy is missing in the final state. He's talking about two capacitors of equal size, as we demonstrated. Hence, per this guy from Princeton, half the initial energy is missing in the final state. Where is the missing energy? Darn good question. So I won't say I've gone through all 42 articles or citations there, but I have skimmed a number of them. And I would say there's, many credentialed people given very detailed, difficult to follow explanations with a great deal of complicated math and figures and charts. To definitively put the issue to rest, it is that with all these credentialed people, there are multiple different proposed answers, and to my untrained eye, none of them are very good, and their stories don't match. So I'll just kind of mention, and one can go back through the literature themselves, and when I put this out, I'll go through the literature in the book. But there's sort of three ideas. The first is that the dissipated energy is dissipated as radiated energy. That's one of the first things. So my first thought, we looked with the small capacitor discharging to the large, 90% of the energy is lost. So that would have to be 90% of your input energy is radiated energy. And my question then would be, well, what can you tell me about this radiated energy? I mean, is it dangerous? 90% of the energy is being radiated. There must be some way to measure it, to quantify it, to say what it is. Where is it? So that doesn't make a whole lot of sense. So if we go down further, another explanation is resistive losses. That's wrong on so many levels, and before this video ends, I will demonstrate why that is wrong on every level. It's not resistive losses, and I will demonstrate that. Finally, another explanation that they put out there is, where am I? Is switching losses. That somehow with the switching there's a loss. And that sounds really nice, but what the hell does that mean? What you're saying then is that the switch is a destroyer of energy. But I thought energy can neither be created nor destroyed. So all you're doing is saying, energy can be destroyed. There's a switch. So, avoid switches or energy will be destroyed. So the whole idea of switching losses is, what does that even mean? So that's no good. So as I said, when I glanced at the literature on this, I didn't see anything like, okay, this is it. I saw a lot of people with, letters after their names disagreeing and putting out things that I'm not, this isn't my ballywick, but it's like, what the heck? That doesn't, number one, these theories that are posited are not consonant with each other, and number two, they really don't explain what was seen. But this isn't the whole of it. It gets worse. It gets a whole heck of a lot worse, and I'm going to explain that to you now. So here from the website Electronics Tutorials, which I think this is Texas Instruments engineers, as far as I can tell, when I look at like that's my best guess. I mean, they have all kinds of Texas Instruments prototypes that they want to sell people. So the people that wrote this up have some knowledge. But this is a simple thing. What is the charge in a capacitor defined as? Q equals C times V. So going back to our spreadsheet, now you see the problem in all its glory. Is the charge in a capacitor is defined as capacitance times voltage. The energy in a capacitor is defined as 1/2 capacitance times voltage squared. So there is a immutable law that energy can be neither created nor destroyed. There is an immutable law that charge can neither be created nor destroyed. Do you start to get it? So Q equals CV, E equals 1/2 CV squared. They both can't hold true. When you alter the voltage, either this one has to be conserved or this one has to be conserved. Mathematically, by definition, both of these can't hold true, yet they're both posited as laws of nature. It's just silly. Yeah, let's go back and put charge in Q, coulombs of charge, into our spreadsheet and see what we get with our experimental values, recalling that the experimental values are not perfect because of all the reasons that we discussed previously, but they're in the ballpark. So for the first one, Q, we had 10 volts, 1 coulomb. Q equals C times V. Yeah, let's just copy, paste, 0. So we start off with 10 coulombs. Paste, paste. We ended up with 5 and 5. We ended up with 10 coulombs. Started with 10 coulombs. Let's do it down here. Paste, 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 paste. We started with 10 coulombs. We ended up with 9.91 coulombs. And again, recall the experimental error with the cap rebound and the differences between the sizes of the cap. Paste, paste, paste. We started with 1 coulomb, we ended with 1.1 coulombs. So within the margin of experimental error, conservation of charge is valid. And that's why I'm saying algebraically, when you know the starting voltage and the capacitance of a capacitor and the voltage and the capacitance of the second capacitor that you're discharging into, you just follow this equation and algebraically solve, and you can know what they're going to end at. So I mean, the simplest example, with the capacitor at 10, they got to both end at 5, and it's going to end up at 5 volts, but you can solve for that. And I put that all in a spreadsheet and whatnot, and that is useful to you because you know exactly what the voltage should end up at. So it's sort of, you're at the situation of like, which is worse? That you can take two 25-cent capacitors, a $10 multimeter, and annihilate conservation of energy every single time you discharge the capacitor into another. You might annihilate it 50% or 10% or 90%, but every time. And then it becomes a philosophical question. Is that more important than the fact that mathematically E equals 1/2 CV squared and Q equals CV cannot both simultaneously be conserved, yet they're both put forth as immutable laws, yet mathematically only one of them can hold? So at this point, I'll let Mr. Spock provide some commentary on a situation where they found themselves in a reality defined by lies and illusions. So here he goes.
Captain, you don't seem to understand. It did not function, but it must function.
Nothing could go wrong, Captain. It should work.
The scientific
You
fact.
just discharge one cap into another.
If the tranquilizer does not function, which is clearly impossible, then a radical alteration of our thought patterns must be in order.
We'll return to the inimitable Mr. Spock in a moment. However, radical alteration of our thought patterns is in order. Before we return to that, the third thing that I said I'd get to this, the third theory posited for why energy was gone was that it was lost through resistance. And I'm now going to demonstrate why that is folly. And when I did this experiment, I have to admit I lost a lot of respect for some of the people writing in on that topic. I have noticed that many of the practical engineers understand this, that resistance never causes a loss of energy or charge. Pretty much by definition, the charge has nowhere to go. All it causes is a loss of power. So what do I mean by that? So we're going to do our first experiment again, where this is going to be charged to 10 volts, and now we're going to discharge it through a 1,000 ohm resistor to this one. So if there are resistive losses, the resistance internally of the capacitor is about 2 to 3 ohms with one of these electrolytics. It's called the equivalent series resistance, and the resistance from the water in there and the wires coming out. But these are fairly high resistance as compared to other kinds, but in any event, it's about 2 to 3 ohms. This is 1,000 ohms. So this is going to be on the order of a 300-fold increase in resistance. So therefore, if there are resistive losses and you've increased resistance 300-fold, this is not going to go 10 and 5. Oh, there's going to be great resistive losses. So I charged this cap to 50 volts and I let it sit there for like 5 minutes. And so I apologize, it's now actually creeping up in voltage instead of going down. So that's what I'm talking about with cap rebound. See, there's nothing connected there. And that's, again, the polarity of the water gets arranged there. But that's not what we're talking about. We're talking about when this is at 10 volts, and I discharged that for like a minute. So this thing is discharged. It's at 0. So what's going to happen when we put this through resistance? You know, when you're putting it through resistance, my gosh, that means it's going to draw off power, and these are both going to end up at like 2 volts because they're all the resistive losses 300 times more than if you discharged normally. So again, the thing is a little bit climbing, and maybe this one was rebounding a bit too. Exact darn same. 300-fold increase in resistance. Now further, I'll leave it for an exercise for the viewer. You could put a 1 mega ohm resistor in there. And just don't leave this thing connected, because this will be a short across the 1 mega ohm resistor in here that will draw off power, but will draw off current, I should say. But if you put the 1 mega ohm resistor in there and connect this and then come back 5 minutes later, and this was at 10 and this was at 0, they're both going to be at 5 volts. And so you've increased your resistance 300,000 fold. And yet there are no resistive losses of energy. Still. And I don't want to belabor this, because, you know, I can step in a gopher hole and you know, just be absolutely foolish. But they're positing resistive losses as accounting for why there's the loss of energy. Yet there are no resistive losses of energy. There's no change in the initial or ending state depending upon whether there's no ohms of resistance or 1,000,000 ohms of resistance. It's just whether the ending state is achieved in a fraction of a second or 10 minutes. So that kind of burns me up. So where are we at now? I mean, I would just say that the cudgel that is used to bludgeon people so frequently when they begin to explore nature is: energy can neither be created nor destroyed. Conservation of energy. We demonstrated with two 25-cent capacitors, and this could have been a $10 meter, that conservation of energy is violated every single time that one capacitor is discharged into another by definition. Further, by definition, conservation of charge and conservation of energy cannot mathematically both be valid at the same time. One of them has to give. Further, we've demonstrated that conservation of charge is validated every single time that you discharge one capacitor into another. So what does that mean? That means that conservation of energy is nonsense. It's garbage. It means nothing. I'm sorry to get a little carried away, but I'm just saying that if we are mistaken about something that's that universally accepted and apparently that fundamental, then, you know, what exactly is our perception of reality? And so I'm gonna end here in a moment with Mr. Spock at the end of that episode where they were in a false reality. But I'm just saying that you know, conservation of energy is violated to the downside every time. In a subsequent video, I'll show you violating conservation of charge to the upside. But just to get back to this, conservation of energy is not a law. It's a lie. And prove me wrong, because I can demonstrate that I'm right, and I can further demonstrate that I'm right simply from what is posited as being valid in terms of conservation of charge. So let's go back to Mr. Spock and end this.
Your mind to my mind. Your thoughts to my thoughts. substance. They will not pass through your body, for they do not exist.
They do not exist.
Unreal. Appearances only. They are shadows, illusions. Nothing but ghosts of reality. They are lies, falsehoods, specters without body. They are to be ignored.